Okay, so the next thing I want to address real quick is the notion of drawing electron-dot structures of compounds containing only hydrogen and second row elements, so stuff like carbon, nitrogen, and oxygen. This is important because most of organic chemistry, if you've come across that term or if you'll actually be taking that class, revolves around compounds that largely consist of carbon, hydrogen, and other elements, most of which are in row 2. Now, to do this, at least the examples you'll be given in this class, really what you want to do is just kind of hone in on the fact that for second row elements as well as hydrogen, there's a certain number of bonds that you expect each atom to form and a certain number of lone pairs to have. So if you go back to that chart where, for instance, it shows that carbon has 4 valence electrons and is expected to form 4 bonds, nitrogen has 5 valence electrons and is expected to form 3 bonds, and so on. The vast majority of compounds that contain carbon, hydrogen, and then other second row elements are basically going to be dictated by that. Now, if you get to larger chemical formulas than, say, the one you see here, ethane C2H6, if we get to something with a lot more carbons and hydrogens, there's actually not a way for you to convert the formula into one and only one correct Lewis structure. So your examples are going to be limited to simple ones, or at least relatively simple ones like ethane here, where given a formula, you can apply the expected number of bonds to arrive at an unambiguous structure. So if you look at the Lewis structure for ethane, especially there on the right, you can see both carbons have 4 total bonds around them, and each hydrogen has 1 bond, and there aren't any lone pairs on any of the atoms, and both of those things are consistent with the way we would expect those to behave based on the table of number of bonds formed on a previous slide. And we'll actually look at an example of this later on. For now, what we're going to go ahead and do is move on to the notion of resonance structures. So for this, we're actually just going to look at an example that seemingly starts the same way as all the other examples that I showed you where we went over how to draw different Lewis structures from formulas. So for this example, we're going to use ozone, which is O3. Regular oxygen is O2. O3 ozone, it's the same stuff that's in the ozone layer, if you've heard of that before. It's also a pollutant if it's closer to ground level, but it plays an important role in the Earth's atmosphere at much higher levels of the atmosphere. Anyway, this consists of 3 oxygen atoms bonded together, so let's see if we can draw a Lewis structure for this. As always, we're going to start by figuring out how many valence electrons we have, so that should be each oxygen has 6 valence electrons. There's 3 oxygens, so that should be a total of 18. Step 2 is to connect the atoms. In terms of what to choose for the central atom, we really only have one option, it's oxygen, so we'll just put one oxygen in the middle and attach the other 2 to that central oxygen. So we end up with O, single bond, O, single bond, O. That used up 2 pairs, or 4 electrons, so we have 14 left. Step 3 asks us to use as many as we can to fill out the octets of the outside atoms, so those would be the left and right oxygens there, I guess. So if you put 3 lone pairs, or 6 electrons around each, combined with the single bonds that we already had, then both of those oxygens on the outside will have 8 electrons each. And if you count up everything, we should still have 2 electrons left after step 3. And so we're going to put those on the central oxygen, since that's the only place to put them. And so we'll have 1 lone pair on our middle oxygen. Now, here's where things become interesting and where the notion of resonance comes in. If after step 4 we look at our oxygen here in the center, we have a lone pair and then 2 single bonds. So we have 3 pairs of electrons around this, meaning we have 6 valence electrons around our central oxygen. Now, obviously, if we're following the octet rule, we'd like to have 8 electrons. So we don't have enough electrons, which means as with previous examples, what we're going to need to do is take a lone pair from an outside atom and use it to form a bond instead of a lone pair. So what we can do is, you can see we have oxygen both on the left and on the right that have some lone pairs. We could use one of those to form a double bond. And so you can see with the rightmost oxygen, we've taken one of these lone pairs and dropped it in between our two atoms so that we now have a double bond here at step 5, which gives our central oxygen, this guy right here, 8 electrons around it. We have 4 pairs, 1 lone pair and 3 bonding pairs. And each of these outside oxygens still each have 8 electrons around them. This lone pair is still accessible to the oxygen on the left because it's sharing it with the inside oxygen. Now, you may ask, and this question is basically a giveaway, that we're dealing with a situation where we need to invoke resonance. Why did we use the oxygen on the left? Why couldn't we use the one on the right? And the real answer is the true Lewis structure of this molecule is actually some hybrid in between using the oxygen here labeled in red and the oxygen labeled in green. So at step 4, we had what you see up there at the top of the screen, and we could use a lone pair from the red oxygen, which is what we did in the previous slide, or the green oxygen. And if you use a lone pair from the red oxygen, you get the resonance form shown here on the left. And if we use not a lone pair from the red oxygen to form a double bond, but one from the green oxygen instead, then we're going to end up with this resonance form over here. Now, the reason why there's 2 Lewis structures that apply to this molecule, which are what these 2 resonance forms, as they're called, are, is because the true bonding situation can't be completely adequately represented by a single Lewis structure. And whenever you have a situation like this, especially where you need to kind of decide where to take electrons from which of adjacent atoms to complete the octet of the central atom in step 5, that's a situation where you're going to have resonance forms of your molecule. And so the true electronic structure of ozone is some sort of average of the 2 individual structures that you see. And for any resonance form or set of resonance forms, what you do is you just write out all the different resonance forms and you put these double-headed arrows in between the resonance forms to indicate that they're both resonance forms. This is not a reaction arrow. Notice that it points in both ways. This is just showing that the 2 Lewis dot structures here are both representations of the correct electronic structure of, in this case, ozone. Now, one way we have to evaluate resonance forms is by calculating formal charges for each of the atoms in any Lewis structure. And in fact, you can calculate formal charges for all the atoms in any structure. It doesn't have to be one with Lewis structures, but we're going to use ozone here as an example. Now, formal charge has this formula that you see on the screen right now, and you might be wondering, why are we going to use this arbitrary formula? And it turns out that if we apply this formula, we're actually going to end up with a number that we can assign to each atom in a Lewis structure. And the value, specifically the interpretation of that value, can tell us how good of a job any Lewis structure does of representing that given Lewis structure. So you can see the formula there, which is the number of valence electrons in a free atom, which, since we're dealing with ozone, these are all oxygen atoms. That number will always be 6, since a neutral oxygen atom has 6 valence electrons. And from that, you're going to subtract the number of bonding electrons times 1/2. You could also think of this as subtracting the number of bonding pairs. And then we're also going to subtract from that the number of non-bonding electrons, so the number of electrons in lone pairs, and we're not multiplying that value by 1/2. And the value that we get shows us in a Lewis structure what the electron density around each atom in the Lewis structure should be. So the more positive the value of the formal charge, basically that corresponds to a lower electron density. And if we have a more negative formal charge, then that corresponds to a higher electron density. So you can see here at the bottom of the screen that oops, sorry about that. We'll get to that in a second. For each of the three oxygens that you see here on the screen, we can calculate the formal charges just by plugging in the relevant values. So for the leftmost oxygen, assuming that we have this structure where the double bond is between the left and center oxygen, this oxygen on the left has a formal charge of 0. This oxygen here in the center has a formal charge of +1. And this oxygen here on the right has a formal charge of -1. Now, what this means is that the oxygen in the center is relatively electron poor compared to the other two oxygens, and in this resonance form, the oxygen there on the right is relatively more electron rich. Remember, electrons are negative, so a negative formal charge implies a more electron rich atom. Now, in terms of interpreting formal charges and what they say about resonance forms, we can look at the formal charges on atoms in a Lewis structure and use that to interpret how good a resonance form is. Now, for pretty much any atom, the best possible formal charge in any Lewis structure is going to be 0, because we want to have it overall electrically neutral. Now, to make this Lewis structure that we have here, we had to obey the octet rule, which is more important than anything to do with formal charges. And you can see that we ended up with an oxygen with a +1 formal charge in the middle and a -1 formal charge on the right. Now, when we look at some other examples with resonance, we'll actually go through and do one here in a few minutes. If you have negative formal charges, you want those to end up on more electronegative atoms, and vice versa. So when all three of these atoms are oxygen, I guess it doesn't really matter all that much, but when we look at an example where we have two different types of atoms in a resonance form, which is something we'll do on a later slide, then I'll show you how we can use formal charges to actually determine which one of the resonance forms that we draw is the best resonance form.